Alright, so how do we come up with this expression for gravitational potential energy? We're used to seeing mgh, but this one looks really close to the Newton's law of gravity, gmm over d squared. What happened to the square here? Well, it's just simple calculus. Um, Remember this from past unit. Work is the integral of f dx. So if we integrate the force function with respect to d, you should see pretty quickly that the squared disappears. They have a derivation, by the way, if you're curious, on page 340 of your textbook. Helps you see where this negative comes from. Partly, what the reasoning behind the negative is for the following. What we're doing is we're actually defining zero gravitational potential energy infinitely far away. Normally, it's infinity, not an 8. Normally, we would, in the past, we've defined gravitational potential energy where it's most convenient, and typically that's on the ground, or the lowest point in the problem. But in this case, we're going to define gravitational potential energy as the point infinitely far away. So what that means is, just like before, if you start out infinitely far away, and you start falling towards a planet or some object, you're going to lose gravitational potential energy, and it's going to turn to kinetic energy, and you're going to get faster and faster and faster. So if you define gravitational potential as 0 joules out here, and you're losing gravitational potential energy, the only way you can go is into the negative numbers, and so that's why that's another reason why this negative sign is here. So for these problems in this chapter, we're going to define gravitational potential energy as 0 out at infinity, and it will be negative, more and more negative as you get closer. Alright, so basically just calculus to get this. So then where does this very similar looking expression for kinetic energy come from? Essentially the same as potential, but without the minus and with a 2 on the denominator. We're used to seeing kinetic energy as 1/2 mv squared. We're going to kind of use that actually to help derive this. And so all we really need to do is realize that if you're, by the way, this is orbital kinetic energy. So if here's a planet, if you're orbiting around a planet, we'll say this is m2, the mass of the planet, you're a little m1, and you're moving in a circle, right? So let's bring back some of the good old days. If you're moving in a circle, your net force is your centripetal force. And then the only force causing you to do that, if there's no air resistance or anything out here, or no engines firing, that is the force of gravity. So we get centripetal force is m, it's the force on you, so m1 v squared over d equals g m1 m2 over d squared. Well, this d and one of these d's cancel, and if we were to happen to write a 1/2 here, of course we'd have to do the same thing over here, 1/2. Hey, take a look. 1/2 mv squared, that's kinetic energy, equals gmm over 2d. And there it is. So a quick little derivation for orbital kinetic energy. Now, if you want to talk about like the total mechanical energy of a system, then we can do that. E total is just made up of your gravitational potential energy and your orbital kinetic energy, and that is just negative g m1 m2 over d plus g m1 m2 over 2d. So this is essentially like -1, and this is a positive half. So -1 plus a half is -1/2. So that just simplifies to negative g m1 m2 over 2d. So here's your -1/2. So total energy of an orbital system is this. Again, very closely related to both of these. that's pretty cool, and we'll use that in some problems. Alright, and what else we got going on in this unit? Oh yeah, escape velocity. So, this is kind of cool. Let's say that you want to escape. You want to get in a rocket and just go off to infinity and beyond, right? So, how fast do you have to leave your planet to do that? So you start on a planet, here's your little rocket, and you go blast off, and just try to get out to infinity. Alright? Well, we need conservation of energy to talk about this, and so we'll make an assumption. We'll say you start off with some gravitational, gravitational potential energy, and you need to start off with quite a bit of kinetic energy, right? If you're going to launch off, you got to blast off with some pretty high speed. But then we say, well, let's make escape velocity just enough velocity so that we come to a stop at infinity. You know, we don't need any more than that. That's overkill. That's just a waste of fuel, right? But just enough velocity so that we come to a stop at infinity. So KE is 0. I really should be careful and put like initial, final, final. You can do that in your notes. I'm just going to be a little lazy here. So our final kinetic energy is 0. But if you remember, we just got done discussing that we were defining gravitational potential to be 0 out at infinity. So this is also 0. That's pretty cool. So, but we also want speed, right? So we're not going to use the new form of kinetic energy that we have. We'll just use the old-fashioned one. And so this is just negative g m1 m2. m2 is the planet over d plus 1/2 m1 v squared equals 0. Add this over because it's negative. Solve for v, and you get v equals the square root of 2g m2 over d. Now these letters in the book are slightly different. They maybe make a little more sense in the book. This is 2g capital M. The book likes to use capital M for a planet, which is typically the type of object you'll be launching off of. I'm going to put Earth in particular, mass of the Earth, over radius of the Earth, because you'd be launching at the Earth's surface, so you need the radius of the Earth considered. Yeah, that's that. All right, and I think that's it for this unit. So I'm going to do some sample problems now that will help illustrate some of the things I talked about, and after that, one more unit to go. Congratulations for making it this far.